welcome. So, in the last lecture, we were talking about how to compute the Fourier coefficient of a function which is defined on Zn, and the number of steps one required to do the simple calculation of multiplication and addition. In a computer is going to do addition and multiplication. So, how many steps needed to compute a Fourier transform, that is very important for many things if you want to compute the Fourier transform precisely. So, what we have seen is that if I take a function f and I write it in terms of the f 0, f 1, f n minus 1 and the Fourier coefficient to be capital F 0 to f n minus of 1, then as a matrix what we have seen, the script f, when it acts on the column vector f 0 to f n minus of 1, this is going to land us into the Fourier coefficient of the function f. And that what we have seen is that it will be kind of the order n square plus 2 n at most. I mean, that is what we can do it if we multiply, if we take each step multiplication as one step and each addition as one step, then if we compute it, this is n cross n matrix, and so we will get of the order of n square at least. So, now, just imagine that if n square and if you have a large data you need to find the Fourier coefficient, then it will take enormous amount of time for the computer to compute the Fourier coefficients. So, there is a clever method given by Cooley and Tukey that for certain cases one can reduce this number of step. Actually, after their algorithm, so life becomes much easier to compute. So, we will see that. So, now what is the essence of their idea? So, now we have seen in the last lecture, this is what is our Fourier coefficient. We can write it in terms of the operator f script f acting on f, we are going to get the Fourier coefficients. Okay, so, now let us play around a bit. So, now I define two functions. I will write f 1 to be equal to, just I will take the odd and even divided. So, this is f of 2, this is 0. So, this, suppose I have n, I am getting 2 m. So, this is f of 2 m minus 2 and 0, and I write similarly f 2 to be equal to 0 f 1 0 f 3 0 like this, then 0, and this is f of 2 m minus of 1. Clearly, if we see f, our function is nothing but f 1 plus f 2. And similarly, what we would like to define the script f 1 to be equal to 1 by 2 m, and this is 1 0 1 1 1, and then this is 0 0 0, this is 1 omega square, then omega to the power 2 into 2 m minus 1, and then again 0 0, and then the last but one column will have, the last column will have 0. This is 1 omega to the power 2 m minus 2, and this is omega to the power m minus 2 m minus 1 2 m minus 2, and we denote similarly f 2 as 1 over 2 m, and then this is 0 0 1 omega omega square, and then this goes to then 0 0 0, and then here in the last column would be omega 2 m minus 1 omega 2 into 2 m minus 1, and this goes to then if we can see that if you are acting f 1 with f 2. Now, if you act f 1 with f 2, that a priori we know that this is equal to 0, and similarly f 2, if it acts on f 1, this is equal to 0, and also notice that f is equal to f 1 plus f 2. So, therefore, f 1 f 1 plus f 2 f 2, this is equal to our Fourier coefficient. So, in a sense what we can see that we are reduce what essentially when I am acting the script f 1 on f, I am, although it is a part of the 2 m cross 2 m matrix, but I can treat that as a function on z m instead of z 2 m. Similarly, for f 2, that means the number of if the number of computing the Fourier coefficient, it is going to be, let us say, if I denote it by for z m, this then what it suggests is that if I take 2 m z 2 m, then number what I need, this is essentially less or equal to, here this is the m Fourier coefficient, here I am going to m Fourier coefficient with little bit of extra multiplication, and so therefore, this is some comparable to 2 times number of m and plus something. So, that what we can easily, you can do it by computing, but we will write it down very explicitly. So, a good reference for these materials is the book A First Course in Fourier Analysis by David W. Kamler. Now, let us look at this. So, now I will say the lemma. Let cardinality of m denotes the minimum number of the operation needed to calculate all the Fourier coefficients of any function on z Z m, then the number I need to calculate the Fourier coefficient for a function on Z 2 m is less or equal to 2 times the number of m plus 8 m. So, the proof one can see it. You take, let us do omega 2 m, I will denote it as e to the power minus 2 pi I by 2 m. Okay. Now, first I need to compute omega 2 m square, and this is omega 2 m minus of 1. This will require how many steps? 2 m steps. Okay. 2 m multiplication. So, this is 2 m, rather to be more precise, 2 m multiplications. Okay. Now, we know that, so if omega m, this is equal to e to the power minus 2 pi I by m, e to the power minus 2 pi I 2 by 2 m, which is equal to omega 2 m square. So, now we can compute the f1 and f2 by at most 2 m addition and multiplications. Now, let us calculate our Fourier coefficient f k. By the definition of that, this is equal to 1 by 2, because 1 by 2 m and this. So, this is equal to f 1 of k, the even part, plus f 2 of k omega 2 m to the power k. Why is that? Now, just you calculate the simple calculation. This is 1 by 2 m, then the summation over n equal to 0 to 2 m minus of 1. This is f of k, f of n, e to the power minus 2 pi I k n by 2 m. This is what we need to calculate. So, this sum I can write it as 1 by 2. This is 1 by m summation over n is equal to 0 to m minus 1 and f of 2 n and e to the power minus 2 pi I k 2 n by 2 m plus 1 by m summation n is equal to 0 to m minus 1 f of 2 n plus 1 and then e to the power minus 2 pi I k 2 n plus 1 by 2 m. So, which essence, if you write this down, then this is going to be 1 over m summation n is equal to 0 to m minus 1. This is our f 1 at n, and then this is e to the power minus 2 pi I k n divided by m, the factor of 2 gets cancelled, plus 1 by m summation over n is equal to 0 to m minus 1 f 2 of n, and then e to the power minus 2 pi I k n by m into e to the power minus 2 pi I k by 2 m. So, this is what precisely what we have written down over there. So, this is nothing but 1 by 2 and then this is f 1 of k plus f 2 of k and then omega 2 m to the power k. That is what it is going to be. So, now as you can see that f k can be computed then at most 1 addition and 2 multiplication. This is 1 addition and 2 multiplication, that is what it is going to. Therefore, hence the cardinality of the number of multiplication and addition required for Z 2 m, this is less or equal to. So, now f 1 I need to get m, because I am computing the I am assuming that this is the number in which I can compute for Z m. So, this is 2 times number of m, then this is the 3 into 2, that is the 6 m, and plus when we are calculating this 2 m multiplication. So, this will give us 8 m. So, that is what the lemma is saying. So, now the number of 2 m. So, now as you can see that if you are taking the 2 m, so we will going to get this. So, now this has a wonderful effect which is called the fast Fourier transform, more popularly known as FFT. Okay. So, what does it say? So, this says that you take this theorem given omega n, this is equal to e to the power minus 2 pi I by n with n I am taking 2 to the power n. This works for particular if our n is of the form 2 to the power n, where n is a non-negative integer. So, n equal to 1 and onwards, positive integer, it is possible to calculate the Fourier coefficient of a function on Z n with at most 4 into 2 to the power n into n, which is nothing but 4, 2 to the power n is capital N, and n is nothing but log 2 to the base n. So, this is a drastical step. Now, for example, if you want to take, suppose let us say, let us compare this. Suppose if I am taking n is equal to 2 to the power 16. Then in our earlier one would like to get that this is going to be 2 to the power 32. So, at least this 2 to the power 32 is equal to 65,536. However, if I calculate this, so this is 4 into 2 to the power 16 into n is 16. That means 2 to the power 16 into 2 to the power 16 is equal to this, and 2 to the power 16 into 64. So, instead of going to 65,536 steps are needed if we just do with the multiplication, matrix multiplication with the f, and then find out all the Fourier coefficients. So, this is a very clever trick and very efficient trick which actually makes the computation possible. So, the proof is by induction. Now, for n equal to 1, now that means what is we are doing in Z 2. So, which is equal to 0 and 1. Now, if you calculate f 0, then this is f 0 plus f of 1. Now, if I calculate f 1, this is of course half of this, and f 1, then this is going to be 1/2 of f 0, and if I am taking 2 divided by 2, 2 pi I which is equal to minus 1 into f of 1, then how many steps it is needed? It will need only 1, 2, and then here 1 multiplication by 1, then addition 2, 3, 3 steps are needed. So, here it is 5 and 5 is less than, definitely if I want to take n equal to 1, then this would be 8. So, true for n equal to 1. Suppose true for n equal to 2 to the power n minus of 1. Then by applying so cardinality of 2 to the power n by lemma 2 into cardinality of 2 to the power n minus of 1 plus 8 into 2 to the power n minus of 1, that is your M 2. So, now this is equal to this is what it's true for this. So, this is lesser equal to 4 into 2 to the power here, this one is 4 into 2 to the power n minus 1 into 2 plus into n, n is this n minus 1 plus this is 8 m, 8 into 2 to the power n minus of 1. So, this if we take this out, then this is 4 into 2 to the power n. If I am taking this out, then I am going to get n minus of 1 plus 1, which is equal to 4 into 2 to the power n into n. That is what, so hence it is true. So, by induction we can reduce drastically if our n is of the form 2 to the power n. Actually, this kind of thing one can do it. Suppose remark, if my n is some 3 to the power n, then what I am going to do is that I will take look at all the cosets like 3k, 3k plus 1, 3k plus 2 and play the same game. So, in that case what I am going to get is that this is 6 n log 3 to the base n. It's now, if you go to for any natural number k, suppose n equal to k to the power n, then what you are going to get is that 2k n, then this is log k base n. That is what. So, instead of n square, we are bringing it down to n log n. That is a real good improvement for the computation, and it must have made lot of crystallographer very happy. Thank you.